week that Melissa Strait was coming to give a talk here, and here she is. She's visiting from Michigan, Alma College. She's here with her student Miriam. They're visiting us to do some bulk properties work, basically with the helium pygnometer with some beads. We're playing with some beads for our Canadian volume-based measurements earlier this morning, and yesterday we were on micro-CT to get some volumetric information on meteorites and other rocks. And Melissa's in particular interested in impacted materials, and she does some really cool work with the Ames vertical gun, NASA Ames gun, to impact materials and then analyze the products from that. So that's part of what we're talking about today. So I'm not going to say any more, just that's great. And
okay. Well, good afternoon. Yes, we won't have them turn out the lights. I've experienced PowerPoints, and I know what my students do when I turn out the lights. So I'm in the Department of Chemistry at Alma College, so I'm a bit of an oddball. As a chemist doing planetary science, especially both the physical processes and a lot of the geological material stuff I've done. But I started as a geochemist. That's what my graduate degree is in. Managed to promote physics and chemistry students to do my research these days. So we'll see if this thing is going to work. Yes. So I'm going to talk about the solar system. We're all familiar with the solar system, ranging from Mercury near the sun out to, this is an old picture, so we still have Pluto included in the sequence. And Neptune these days. The history of the solar system, of course, starts with the nebula that was originally present. That eventually then condensed to form the modern solar system. Many of the materials that we work with in planetary science that wind up being asteroids and comets probably are a combination of some of these kind of materials from the early solar system. So in the solar system particularly, the bodies we know we have samples from, we know for sure, we have samples from the moon. That's the only place we know we have samples from an extraterrestrial body. We're fairly confident we have samples from Mars, but I can tell you, back when we first started proposing these things being from Mars, I was an office mate. I was a lowly graduate student stuck in a corner of Don Bogard's office, and he did an interview with some magazine and was telling him all about them being from Mars, and came back and would say, it's all bogus. So some of the scientists who do these, especially in the early days, weren't all that confident they're really from Mars, and we won't know until we actually do a sample return. And of course that applies to where we assume the rest of the meteorites come from, which is the asteroid belt in various places. But again, we haven't done a sample return, so until we do that, we won't be confident in where they come from. But those are pretty much the three bodies and the kinds of bodies in the solar system we think we have samples from. This is the new definition of the solar system. So we have removed Pluto and put it down here in the dwarf planets. So the two kinds of materials we tend to have available from the solar system are the asteroidal rocky bodies, and then from comets we know they have rocky cores with the very fine material that makes up most of the bulk of the rest of the comet in the tail and the coma around and the planet. So from this, we get the various kinds of materials that, as planetary scientists, we work with. Meteorites and cosmic dust. Meteorites, us in the community call God's gift to science, because we don't have to pay to get them. God just gives them to them. Of course, things like cosmic dust, then we have to go out and collect. But we have this wide range of materials that we're working with a wide range of composition. And it's the difference between these two kind of materials that leads into kind of part two of my talk when I get to talking about what Phil is enamored with the impact stuff. But in reality, I started with meteorites. I started studying meteorites. So here's the primary kinds of meteorites that we divide meteorites into: irons, stony irons, chondrites, and then the chondrites, which include the chondrules that we study. We have done a lot of chemistry and geology of these materials over the years, but we're just now finding maybe there's some other kinds of physical properties that might be important in helping us interpret what's going on. So we start with part one of the way I've been working with this. I started as a nuclear chemist doing neutron activation analysis, but then I wound up at Alma College in the chemistry department with no equipment, no money, and basically no time. And so I did a NASA summer program where I worked with Dave McKay at Johnson Space Center and got introduced to this really cool program, which was shareware. So me as an institution with no money, it was wonderful. It's free. It's available off the net. And the year then, I had money from the grant I was on, and I spent the summer purchasing various kinds of this image analysis software to use to do the kinds of work I wanted to do. And I sent it all back because NIH did everything I wanted, and in some cases better, and it's free. It's no longer NIH. When they first developed it, it was a Macintosh-based program. Apple here. There was no PC version. They kept it in the Macintosh realm. They eventually came up with a PC version, but at the same time, Macintosh moved to System 10, which means they had to completely restructure it, and so now it's called ImageJ. And in my mind, as an experienced user with NIH Image, it's not as good. I liked it much better in this version because we had more flexibility with doing some of the image work with it. But I've switched over and used this. So my original work started with the lunar agglutinates with Dave McKay, who was a big boom guy. We were interested in measuring the abundance of these very fine nanoparticle-sized iron blebs. And so we had been working with the scanning electron microscope with backscatter imagery and using NIH Image then to evaluate to see if we could measure the abundance of these little teeny blebs, because they are very bright, so grayscale, they differentiated from the rest of the meteorite, so we had ways to get at doing this. The frustration he had run into when he first used it was that every single image you have to adjust slightly differently, so it's time consuming and very tedious, and he was hoping to come up with some very elaborate computer push the button and it does it for you. 15 years later, I'm still doing it manually, looking at every single image and having to adjust the grayscale range very slightly to select what I'm looking at. It can't be done automatically. There's just too much variation in the images and the samples you're looking at. So I'm still doing it the same way, but I'm patient so I can do this. Okay, in the same lab, one of Dave McKay's tech people was Kathy Thomas-Caperta, and you all know her from the Life on Mars stuff. While she was doing that in one half of her lab, I was working with her at exactly the same time, and we were interested in looking at porosity in cosmic dust. So these are transmission electron images, and part of the problem we had with this was how do you define the edge of this sample, and therefore to measure porosity in the interior, you have to know where the edge was. So that was kind of the problem we ran into in the end. We were also trying to do some microtoming and develop slices to try to create a 3D image of the cosmic dust particle. This was back in the early 90s when a lot of this fancy software today that's just a drop of a hat, it didn't exist. But NIH Image had where you could take a stack of images and create a 3D image, and so we were trying to do that. The microtome sections weren't quite good enough and didn't have quite enough overlap. We were never very successful. But while I was doing this and presenting this work, I was at a conference and Guy Consolmagno walks up to me and says he thought this program was cool and had some ideas for ways to use it for some projects he was trying to get started at the Vatican Museum using their collection of meteorites. So one of the projects I got involved with him was measuring, this is a Martian meteorite, we were trying to measure the sizes of the microcracks in the meteorites to see if they were big enough to put bacteria in so we could transport bacteria from Mars to the Earth in these Martian meteorites. And this, of course, was shortly after the Life on Mars stuff came out, so we were trying to figure out ways that we could get life back and forth, and we knew we had these samples we thought came from Mars. And we did these. I could use my image analysis program, measure these cracks, and bacteria can't fit into there. So they were doing some experiments in the astrobiology section out of Ames to see if they could get the stuff inside the rocks and in there. But in the meantime, what Guy was really interested in, he's working with Phil Bland in England using Mossbauer spectroscopy to measure weathering in meteorites. And we realized that when you look at these, I can tell the cracks in these images that are filled with the weathering material as well as the cracks in the images that are empty. So this turned out to be a really clever way to get at measuring porosity in these samples that have been weathered. Because, of course, weathered samples using classic picnometric techniques have much lower porosities than non-weathered. And when Guy would do some calculations and estimate the amount of weathering based on their Mossbauer techniques, he could get an estimate of how much of the porosity was filled. All I had to do was look at it, measure dark cracks and measure light cracks, and I was getting numbers that corresponded to what he was calculating. So we moved from that into just looking at porosity in general, and at the same time we started working with Dan Britt at the University of Florida, where they were doing the porosity measurements on whole rock samples using picnometric methods, and the guy was doing the beads back in Rome. And I was doing the imaging with the thin sections. And over the years, we did a whole slew of ordinary chondrites, and we tended to get really good agreement on our values and between the picnometric and the thin section methods. And so we've continued to do this work. But slight sidetrack beforehand, how do we measure porosity in a thin section image? You take a backscatter electron image where you have high contrast between the metal grains. You can actually do some modal analysis this way too. I've done some of that. But the porosity tends to be these dark spaces, either filled with epoxy or completely empty. So it tends to be the dark pixel range down here on the range. So I measure the whole image. I can calibrate it. I don't need to, so I can just count pixels. Then what I do is I select the pixel range where the red stuff fills in the cracks, and this is where the estimation of the error comes in, because I can move this selection range up and down and make the red bigger or smaller, so I have to. You can't do very many at a time. Your eyes get tired. You get frustrated and fed up with it. So you do 4 or 5 images, and then you go take a break, and you come back and keep yourself fresh. But it's just filling the red into the pore space, counting the number of pixels that are red, and then the computer records those two pieces of data, so you just do a simple calculation of the number of pixels that are red divided by the total number of pixels gives you the percent porosity, the percent empty space in that image. And so it's a real slick, easy way to do it if you have access to lots of backscatter electron images. The first problem we had when we started doing this was, well, how do we validate this? How do we prove that what we're getting on this computer method matches the ways other people do it? So we couldn't find any porosity standards. They just didn't exist. So we were trying to find something where we could measure it and confirm the two methods. What we finally found in the back of the geology book, these circles that were used for field geologists to estimate things in the field, not necessarily porosity, but if you look at it, it has about this distribution, it's 35% or 20%. So we thought, okay, this is good enough. And so we used the given values out of the book. Then I applied the National Institute, the NIH image method, where you count the black pixels versus the whole circle. And then I took this grid and I laid a piece of grid paper over it, and I literally counted squares on the grid paper, and it turned out these two methods agreed very well. The numbers given in the back of the book tended to vary by 5 or 10% plus or minus, so they weren't, they were purely for visual estimation purposes. So we really still haven't gotten a good way to really validate this unless you call cross-method validation. So then the question is, well, how many pictures do I have to take to get a good estimation of the thin section? And also, are there variations across the thin section? So is one end different than the other, are the sides different than the middle, things like that? That was the first question. We've now expanded those questions. So I had this, yes?
Couldn't you write, I'm sorry, I know nothing about this. Couldn't you write just a simple computer program that filled in some fraction of the pixels?
Yes.
Just like made a circle and put dots in it or whatever?
Oh, for a validation? Yes.
In other words, you could make those and know they were correct.
Yes, you could. We had validated things various other ways in the meantime and just haven't gotten back to needing to do that. But if anybody ever questions us, yes, that's probably what we do, is take some sort of artificial known quantity on a piece of paper and measure it. So I was working on this meteorite called Kinginia, LLL5, and when this question came up, so I wound up taking almost 500 images of it, ranging from about 80 times magnification up to about 500 times magnification. I processed every single one of those images. So, this is the manual looking at each one individually, adjusting the grayscale range to get the porosity and adding all the numbers together. So this is very early in my work, and I was still patient enough to do 500 images all at once. We got an average of 4.7% plus or minus 0.2%. It ranged from 2 to 8% with a nice bell-shaped curve. When they did the same sample with helium picnometry on 3 different hand specimens, they got 4.7, 5.5, and 4.1%. So we're falling right in that same range, and so we have agreement across the two methods. we decided then how many images did I have to count to get my 4.7 plus or minus 2%, and it turns out it's about 30 to 50 images, so I don't need to do 500 anymore. I do somewhere, depending on the size of the thin section, how much material is there, somewhere between 30 and 50. I say randomly selected, that's the way it's supposed to be, but I'm too organized and I can't do random, so I kind of lay a general grid. I know how big it is, I kind of survey it with the SEM, then I say, okay, I'm going to do these strips, and every so often I'm going to take a picture and keep it relatively random. And we get really good agreement with the helium picnometry. So this is the early set of data comparing hand sample porosity and the point counting porosity. Most of them fall on the line. There are a few over here. When we look at them, as we expand it out into other kinds of meteorites, the ordinary chondrites still tend to agree the best, but within the ordinary chondrites, you notice there's a few down here where I'm saying they're all close to 0%, and helium picnometry is getting anywhere from 3 up to about 15%. I thought, what the heck is going on there? Everything else agrees with an error on my correlation line between the two lines. So I went back and looked, and this is what those early images I was working with looked like. I'm going, oh, no wonder my values are so bad. Those are absolutely atrocious SEM images. I didn't acquire them. They were provided for me in the early days, because I don't have an SEM at Alma College. This is what we're acquiring now when I do my imagery. So I can see why I got absolutely atrocious numbers, so I tended to discard those from my data set and have gone back and re-imaged some of these with the way I do it. In addition, in doing all these observations, there's a variety of problems that crop up. People tend to say, the numbers you get off your thin section, we don't believe, because when you prepare the thin section, you damage the thin section, you remove porosity, you add porosity, and it's just no good. And I say, okay, I've been doing this for 15 years. I've learned to recognize that when you do it at the edge of the sample, you tend to get damage around the edges, which increases the porosity, so I avoid the edges of the thin section. I can look at this and say that is plucking from the grain. I'm not going to count that as porosity. I know what it looks like. Some of the images that I get have big metal grains in them. This is a randomly selected location. I can't discount it because it's a big metal grain, but it obviously has less porosity than other areas of the meteorite. This one I would have to include. But some of these places here I might doubt because maybe that's damage or shifting when they process that section. There are obvious places where we have big plucks. Grains have been plucked out when they're prepared. I see that, I say that's a pluck, I don't count it. There are interior holes, however, you have to be careful to differentiate the holes from the plucks. This is full of epoxy. And I've learned you have to count the holes that are full of epoxy. And recently I've been doing some work where I found places that look like this. You can see the base of the thin section. And so it's something that's been plucked out of there, but I find places where you can see the epoxy starting to fill in this area, but then it just kind of quits in the middle. So I've come to the conclusion that there's not as much damage in these thin sections for what I'm doing as people seem to think, and that I've learned to recognize what to count and what not to count, and continue then to get good agreement for the most part. We had a group we did with the Untitled Chondrites. I did my, and you can see one of them agrees reasonably well. Two of them are fairly far off. My numbers are low compared to what they were getting with picnometry. So I went back and looked at those. And I say, okay, here's a piece of some Untitled chondrite. And I got to looking at this and I went, idiot. You're the one that did your PhD thesis on Untitled chondrites. And all these little holes here used to have oldamide in them. And oldamide is a water-soluble mineral that holds all the rare earth elements, which was what I was analyzing, but it's water-soluble. They've been sitting in a drawer in Michigan with high humidity, and the oldamide's gone. So I go back and I count these little holes that I discounted as being plucks. Well, they're not plucks. They're places where grains used to be that have dissolved away. And when you add those in, the agreement comes into line with their seeing with helium picnometry. So I've learned. And then just last year, one of my colleagues doing the picnometry made the observation that all the other meteorite classes they've looked at, as they get weathered, the porosity goes down. But the Untitled meteorites, as they get weathered, the porosity goes up. And I immediately wrote and said, well, These have all this oldamite, and some of them have a significant amount of oldamite, up to maybe 2%, which is the number they're talking about, and your oldamite is weathered away. So your porosity is going to be higher than expected because you've lost a mineral grain. And finally, then, the biggest problem we still have remaining is the carbonaceous chondrites. And this is a huge problem. I measure them up to maybe 5%. I can get a few individual images that approach 10%, but they tend to average less than 5%. Helium pycnometry shows 20 to 25% on a regular basis. You look at the picture, that is not 25% porosity. And if you look at that particular image is 3.2% in porosity, which was high for that particular sample. Here's some more samples from that same meteorite. This is the edge of the thin section, so I didn't count that. But even when you go back and recount all this internal stuff that initially, well, maybe it's plucking, I shouldn't count it. When you go back and count it, you can maybe get up to 10%. There is not 25% porosity in these meteorites that you can see. So I have carbonaceous chondrites where this one averages to about 2%. Helium pycnometry says about 23%. That's what 20% to 30% looks like. And it's not what we're seeing. So this is still a big question that we have in measuring these carbonaceous chondrites, is where is the porosity? Carbonaceous chondrites are full of phyllosilicates, which are layer silicates, and we've proposed, well, maybe the helium, when it goes into the layers of the silicates, which isn't true porosity, but it's going into the rock. But now Phil has told me that it comes right back out fairly fast, so maybe that's not the solution. But a couple of years ago in the spring, I was working on a new sample in a different project where I was comparing porosity not across the thin section, but how many thin sections, are there differences between thin sections? So I acquired a piece of chain purr, which is an ordinary chondrite, and I did my usual imaging, but I was working on a microscope where I had, a little bit more time and flexibility to work with, and I lowered the magnification and said, let's do some SEM maps. That's a real hole. And so that thin section on that sample has up to 27%. So I'm suspicious that some of the porosity that we're seeing in those carbonaceous chondrites, some of it may be the very nanoscale porosity. It's definitely not the microscale porosity we tend to see in the ordinary chondrites, but I think a lot of it is these big macro scale voids that when I measure on a thin section, I look at this and say, well, it's a big plot where the edge of the thin section or something like that, and I don't count it. Now I've learned that you have to go back and take these big maps of the whole thing, and then I have to correlate where this picture is on this section and say, oh, that's the tail end of one of these big voids. I need to count it. And so I need to go back and redo some of my carbonaceous chondrites, not only at higher magnification, but also at lower magnification, see if I can find more of these voids as we're looking at. And then, of course, what I was doing here is trying to approach it from the other direction. Yeah, this is not damaged. That's a real hole. It's full of epoxy, so it was there when they made the thin section. It may be squished or pulled out a little bit, but it's real. So I was down here, over here to work with Phil to use the micro CTs to see if we can get this in three-dimensional imaging. I have another friend that's doing it with X-ray tomography, and seeing if we can get these 3D images to see if there is this macrovoid porosity present in some of these whole rock samples. I think at this point that we need to do the helium pycnometry. It's quick and dirty, easy to do. We need to do this kind of stuff just so we can see what the porosity is looking like in the meteorites. And we need to start doing more of this 3D imaging. It doesn't have the same kind of resolution, so we can't get down to the same level. But I think we need to be doing all three. And so people tend to give me a hard time for continuing to do this work. But I think it's important because I think we need to know what the porosity looks like. So where do we need to go? We need to continue to work to see if there really are variations with meteorite type. You're seeing them with pycnometry. I want to look at what the variations look like and look at more meteorites. I'm interested in figuring out when the microcracks that are pervasive in the ordinary chondrites are placed in the meteorite. Are they primordial? Did they occur in a secondary fashion during breakup, transport, or impact on Earth? Or are they being introduced in thin section preparation? The last one I know we can cross out. I have seen a 3D map of an ordinary chondrite with the X-ray tomography where you can see the network of microcracks in the sample. So we know that this is, it may be a minor contribution, but it has to be somewhere in one of these other two locations. And so continue to look at the porosity. Do some lower magnification and SEM imaging. I'm also arranging it with Michigan State in their high resolution electron microscope to do some very high resolution imaging to see what we can say. And then I'm really excited to get our results, which we're going over this afternoon to collect for the micro-CT work we did yesterday. I'm really excited to see what we got. So, part 2. I've been doing these measurements with this program, and I have another friend who is doing some impact disruption work, and he generates these little slides full of holes, which we can measure using my program. So he asked me if I might be interested, wrote me into my NASA grant, and supports my student in the summer. So I've gotten involved in this impact disruption work, and as I've worked with it, I've realized we need to start doing more work with porosity on these samples that we're disrupting. So one of the things I was doing here was looking at some of the samples that we had disrupted with the NASA Ames gun and seeing if the porosity is different before and after impact. So this project started with the idea that asteroids are the source of meteorites, comets are the source of cosmic dust. This is what had always been assumed. There was enough differences in composition and structure that people thought this is just the way it was. So George's idea was to take meteorites, which are our asteroid analogs, and disrupt them and see what distribution of particle size we get, and is there a difference in composition in the different particle sizes. So in the meantime, then we started doing asteroid visits. So this was deep impact. I know when this was going on was the first summer I had a student, and we were, after having gotten information from the NASA Ames experiments, we were terribly afraid that they were going to send this big bullet towards this asteroid, and it was going to go right on through because it was so, it was a rubble pile, so there was nothing to stop. So we were afraid that was going to happen. Luckily it didn't. We got some interesting information. So we go to the vertical gun in Ames. This is in its vertical condition. This is the chamber where we set up the experiment. Then the gun is on these two arms. The gun goes on up here. It's got about a 30-foot long barrel. They then can lower, they use it in this position for the crater studies they do, so we all those cool crater things when they're making craters in sand, that's the position. We lower it down to a 45-degree angle and send the bullet then into one of these ports along the side. Inside the chamber then, we have our meteorite, or when they first started doing the work, they were using terrestrial rocks because nobody likes us. We don't do anything to the rock. You give us your rock, you get it back exactly the same, except it's in 800,000 little teeny pieces instead of one big rock. And they sort of don't like that. So to prove that this was going to work, George started with, I was with him when he collected the Hawaiian basalts from Haleakala, and then he got the rest of them from a road cut in California, some California greenstone, so both original basalts and weathered basalts. So he could just prove, yes, we can hit the rock, yes, it's going to disrupt, and then he designed these targets. This is just a piece of foam core. These are various thicknesses of aluminum foil. These are mounted in slide mounts, and then we just tape the other piece, a big piece of thick foil, to the bottom. And then these are air gel cells, so we can generate the holes in the film and measure the size of the holes, which are reflective of the size of the particles that penetrated the film. We can compare energies between thick films and thin films, and get sizes and shapes of particles and get a mass size frequency distribution. And then we can also collect particles in the aerogel, and George takes those to Brookhaven and does chemical analysis of those to look at the composition of the bigger particles versus the smaller particles. So this is what the experiment looks like. Give me a minute to load it up. It's a big file. This is a video file showing a disruption in the gun. The first time I went, they had just acquired a new camera, which shoots 1 million frames a second. We shoot it at 250,000 frames a second and can collect about 100 frames. So the very first portion of the impact is what we can collect. We have other cameras that operate at slower speeds, and this is a video from the slower speeds. So we videotape it from all kinds of different angles and get all kinds of different information. So let's see if I can get this to, there, oh, no, that's bad. Let's go for So I'll play, I got another one, I'll play it too, but you want to watch first the rock, the bullet hits it, you can see it shattering. You want to watch the target. And then these are the sheets that we put in the chamber. I tease my research students, you know, I'm a woman as a chemist, and I tease them that as a woman chemist, I went into science so I didn't have to do housework. So what do I spend all my time doing? Washing dishes and sweeping. So Miriam got to sweep the chamber up every time we did one of these shots because you got to clean out all the old, we collect all the particles. And so my part of the project then is to not to acquire the aerogel cells, but to acquire all these films. And we bring them back and we scan them and use NIH image then to measure all the little holes in the film. And then we also sweep up all the solid material and bring it back, and she gets to weigh it all. So we get it from very small to very large size distribution here.
I don't know if this was just, you know, because the way the video was or because the camera was moving, but it looked like your target, the white, big white
It
thing, was moving.
It does. It
So
flexes.
how do you account for the impact energy for the fact that it's not a, you know, a recoil of a, it's different if you recoil like this than if you go.
We're not
Right,
counting.
isn't it?
We're not counting the recoils. We're counting the holes.
Oh,
The
you're
actual
counting the-
penetration. We're actually counting the actual penetrations.
Okay, so the fact that it's moving doesn't affect what would
It
penetrate?
does. It does. But in the general scheme of things, it doesn't affect it enough to change what we're looking at. Yeah. So let's see. Is the next one? Let's see if we can get this one. Oh no, that's not the right one. Here we go. So watch the rock, and then look over and watch the change of the target. Oops. We will only get to watch this once. There's the cursor. There it is. Okay, now it will go. No?
Try clicking.
Yeah, I think just
If you click and do it, okay.
Where's the cursor?
there it is. Okay.
Try again.
There it goes. And what we should be able to monitor the particles and watch them actually penetrate the foil. But I have watched these numerous times, and I have yet to pick the particle that actually hits the foil. They usually pass by. I know there's ones out there that you can see, but I've also managed to miss them. Now, there's the other. There's the other one. So we take the foil back to the lab and scan it into the computer, and this is the data, what the data looks like. And an NIH image has an option where it can literally, you click a button and it will measure every single particle in the screen. It just sends a beam, basically rasters a beam across. It's not what it's really doing, but rasters a computer beam across. When it hits a change in intensity, it travels around that object and reports the diameter for that object. It calculates the diameter. So we can measure diameters for all these particles. We convert those into volumes of the particles, assuming they're spherical, and then using the density of the rock we're working with, we can convert that into a mass. And so we get diagrams that look like this, mass frequency diagrams. This one is still in particle size rather than mass. So starting from the very, very tiny particles, so we're generating both the size frequency and the compositions of the cosmic dust, as well as the size frequency and the compositions of the meteorites from one impact disruption of one meteorite. So we're of the current mind that probably cosmic dust and meteorites all come from the same materials. They're just representing different size frequency populations of the impact out in the asteroid belt amongst comets and asteroids and everything else. All of them have a fairly similar diagram, but some of the slopes change with different kinds of meteorites. If you combine the foil data with the actual masses of the actual particles. They overlap very nicely, and she says she has some newer data that's even better. So we can extend the range from masses of 10 to the minus 10 all the way up to masses that approach 50 grams. And so we get this wide range of data we're representing here in these shots. So the current status, I have a little video that we're going to have to switch over. It wouldn't run in the program, so I'll run it separately. But the current status is we validated that this procedure works with a bunch of original terrestrial trial runs. We've done a wide variety of terrestrial samples. We've done ordinary chondrites. We've done a couple of carbonaceous chondrites that people have volunteered to donate to us. And we've come across a couple of problems recently. There is a distinct difference in the shape and the size frequency diagrams between ordinary chondrites and carbonaceous chondrites. So we've done lots of ordinary chondrites. It's easy to get a hold of those. But there aren't very many carbonaceous chondrites people will let us shoot. So how do we get more carbonaceous chondrites to work with? And then when we start looking closely at those foils, we realize that, yeah, they're all full of holes, but there's a lot of little dents where things hit the foil, but they bounced off. They didn't actually penetrate it. So those are more particles that are in the population. We don't have any information with the flexing. You've got more problems with that. But is there a way we can count those, just to get an idea of how many more particles are present that just didn't have the energy to penetrate the foil? So, starting with the hole versus dent project. That was the project that Miriam got assigned when she started with me, and doing both visual in the microscope, doing various kinds of scanning to see if she could do it with a computer, and it turned out to be an absolute pain in the neck. We couldn't develop a good computer technique because the aluminum foil isn't good enough. There's too many defects in the surface of the aluminum foil. It's hard to tell holes from dents when you scan them. It's hard to tell, are you looking at just a polishing scratch in the aluminum foil, or is it something real? And doing it in a microscope, that's a manual technique. You kill your eyes, and there's hundreds of dents in these foils. And so last summer, we had a new project at Alma College that gives incoming freshmen an opportunity to spend a week on campus doing a research project. And my colleague in physics had one of or two of these students, and he does string theory research, and thought, that's not really something you can do with two incoming freshmen and accomplish anything in a week. But he had come to our talk at our presentation earlier in the summer at group meeting and had suggested this carbon paper method. So he came to me and said, could we work on my project with his students? So his students came, and we developed this little project to look at ways to design detectors that use carbon paper as the detector, so when the piece is hit, they create a carbon paper mark. Our first problem was finding carbon paper. They don't make it anymore. But you said Alt, Tab. Oops, what did it do? So we developed these targets that are pieces of carbon paper mounted on various different materials. They did a lot of practicing over the course of the week with slingshots and throwing things and various ways to project the particles. And I'm going, I have another project I do with the gun club. Maybe we can get somebody with a rifle to shoot a rock for us and set up our targets around it to see if this works. So I contacted the local gun club and said, oh, what are you doing? And finally, once I explained it to them, I said, cool. So we agreed to do it. I grew up in Oregon. Just like George collected his Haleakala basalt along the side of the path, I have a whole bunch of Columbia River basalt that I used to collect just by stopping along the road, driving various places at home. So I had a big hunk of Columbia River basalt, which we set up out there at the gun club. We put our various kinds of targets around, and our professional shooting person, I don't shoot, so he shot. Watch the rock. Missing the dialogue, which is, fire in the hole! Birds tweeting. Spontaneous applause. And we generated just enough little marks on our targets that it's going to give us a place to start with. And so I told the 2 research students who worked on this project for a week at the end of the week that we gave them an extremely poor view of research. Because their project worked, and it doesn't always work. So they're all anxious to start up and do some more work, and I'm terribly afraid that what they're going to get stuck on is something that's long and boring. So now I do Shift, Alt, Tab, Tab.
Yeah.
Yes, okay. And then I can close this window. So that was looking at ways, potential ways to measure dents. The other thing we're interested in is looking at these hydrous meteorites, so we'll click through that. So I had a bomb in my lab, and I told George, well, if we can take an ordinary chondrite and put it in the bomb, and some people had done some work with thin sections, where they did a thin section in a bomb like this at a slightly high pressure, slightly elevated temperature, and fairly basic conditions. They managed to convert all their silicates into phyllosilicates, which is what's indicative of a carbonaceous chondrite. So I said, well, I've got a bomb, and I've got an oven in a corner that I can just stick things in. So we loaded a piece of ordinary chondrite in here, in the Teflon part of the bomb, slightly basic conditions, 150 degrees, 1 month, 3 months, a year, and I have 3 still in the oven. They're now going on 1.5 years. And so then when we take them out, we slice them and then start doing FTIR surveys across the surface of the rock, and we were looking for the presence of this OH. Just, is it developing? We haven't done any calibration yet. We just want to know if this is working yet. And then we're also going to start doing some detailed looking down here for the phyllosilicates that are forming. So we think that we're getting some hydration in the very, very thin surface in our 1 and 3 month rocks, and I'm anxious to get back and look at my 1 year rock. But my student doing the work went back to doing turtle work instead of planetary science work, so I lost him. Problem with small schools. So where do we go? We need to continue to disrupt meteorites. If we're going to be successful with my artificially hydrated samples, these are going to be very small rocks, and the last time, 2 times ago, we went to the Ames vertical gun. We were trying to shoot 30-gram samples, which are about this big, and didn't hit them. Sometimes we could ring them and they'd swing in the chamber, but we were having a hard time hitting them, so we need to learn to hit those small samples. We need to continue to work to find a less stressful method for dents. We need to successfully hydrate a meteorite, and I think then we start correlating what we're seeing in porosity pre-impact and post-impact. So some of these samples we stuck in the micro-CT. I'm really anxious to look at what happened to the structure of the porosity in these rocks after we've impacted them. And I think that the coolest thing we did was 2 years ago when I went to the Ames gun. George was interested in looking at some highly porous materials, and so we were shooting pumice. And we hung this big, huge piece of pumice in the chamber, and we shot it with a regular-sized bullet at a regular velocity, so with a normal energy. And when we finished, the big piece of pumice was hanging in the chamber with a little hole in it. And last year, we did it again, and that's the piece I have with us that we put in the micro-CT, that we shot twice. And after we shot it the second time, we still had the big hunk of pumice hanging in the chamber. So these highly porous materials react differently to impact stress than the more dense, solidly structured materials. And that's going to have a big effect on how we think about studying planetary materials using remote techniques. If we're going to continue to shoot bombs at them, we're going to get unexpected kind of results because they're going to interact differently. And as we start thinking about, the common people always ask me, why are we doing this work? And I say, well, what about that asteroid that comes flying and is going to hit the Earth? And the idea is always to shoot it with an atomic bomb. And 2 things are going to happen. It's going to fragment it into 8 zillion little pieces, so we're going to get 8 zillion little craters instead of 1 big one. Or we're going to shoot it with an atomic bomb, make a little hole in it, and the whole thing's still going to hit the Earth. And we need to know more about the nature of these materials and how they react to impact, both for those reasons and then for studying what's going on out in the asteroid belt for our kinds of reasons. So I'm interested in seeing the results we generated yesterday with our 3D results, and then I need to start doing some more 2D results on the post-impact samples to see what the porosity looks like in 2 dimensions in my classic SEM imaging method. So I want to finish up. How much time do we have? What's the clock?
5 minutes. It's 4 after.
Okay, I want to spend just a few minutes finishing up. You've been wondering what all the stuff on the table is. I'm talking about where we find meteorites. Well, for most people, you find them in your backyard. And I'm the person in Michigan that gets called when you find a meteorite, and I get stuff that looks like this. I had a woman drive up 2.5 hours to Alma last week with 2 pieces of slag that she was sure was a meteorite. So there are better places to look, and it's called the desert. Hot deserts like the Sahara in South Africa, and cold deserts. So I got the opportunity in the 2000-2001 field season in Antarctica to go collect meteorites. So this is a Weddell seal. There's the airplane taking the first half of my field party out into our field area, which looks like this. This little black, I love this picture because that little black blob right there is emergency survival gear for 3 people for 3 days. And we left it in a pile and walked away from it. You don't go very far and it doesn't look very big. We worked in a field area called Meteorite Hills. It was actually named by the first field party in Antarctica who went to this region, who happened to be led by the man who first told me about the Antarctica program. So it's all very insular and everybody knows everybody else. So we were up on the edge of the Antarctic Plateau. These are a couple of glaciers coming down into the Ross Sea, and we were in these hills in between. And that was our field camp. You can see the tents and the snowmobiles. There's our fuel dump over on the side. This happened to be a day that we weren't working because we had a little bit of snow, covered up all the meteorites. Workhorse, the snowmobile, so that little flag there, Miriam was saying, oh, that's such an old pennant. I'm going, but that is the one in the picture. So everybody knew who I was because I had my pennant on my snowmobile. We all lived in these tents. We kept our gear outside. Everybody says, well, what did you eat? All that icky field rations that you get when you go to field camp. No, we had freezer. If you can freeze it, we ate it. So we ate really good. We go out then on our field snowmobiles and we do some surveying in the areas, decide where we're going to go. Sometimes we would do patrolling on foot. Most of the time we just patrolled around on our snowmobiles looking for dark rocks on top of the ice. And they, as you can see, they really stand out. And so we would find a meteorite. We would do some initial characterization of it. We would do some measuring. We would GPS locate it. And then we would collect it in the appropriate way. And in my field season, we collected 758 rocks, of which 749 were meteorites. So they talk about doing this with robots, and the robot success rate is about 50% meteorites. So the humans are much better at recognizing these things. We mark them with these flags, and so you can see we had a really good season. We had a 150 meteorite day, and so we got ahead of collecting them, of the GPSing, so we left all our flags up so we could go back and GPS the locations later, which you can see how closely together they're spaced on these big ice fields. There's every little green spot is a rock we collected. Most of them are ordinary chondrites, but we did come back with a few that I'm not seeing appear in the literature, interesting kinds that people are starting to work with. There was field camps, so we do the collection on this blue ice where the snow cover has been removed, and it's ice that's coming up from below, and so the wind is ablating the ice and just leaving the meteorites behind. So you can see the particular concentration we had in this little valley here, which was this location here. You can see how cold it was. There's my parka right over there. My hat's off. I've got no gloves on. We were walking around on foot, and it was particularly warm. We were having trouble slipping on the ice because there was just a little thin layer of ice, so it was a particularly warm day. We had a particularly warm season most of the time, so a lot of times we did a lot of work without a lot of our gear on because we were dressed for -30, and it was all of -10. The coldest it got was -20, but usually somewhere in between. The other thing people always ask me is if I saw the Aurora Australis. No, but I learned to tell time by which side of the tent the sun was shining on. So if it's there, it's 3 in the morning, and if it's there, it's 3 in the afternoon because the sun never sets. It's kind of cool. And so I'll finish up by thanking a long list of people, the people I've done all my external work with. So my early John Annexted, who turned me on to Antarctica, the people I've worked with at Johnson Space Center, Guy and Dan with the Porosity work, George and Dan. So I work with 2 Dans with the impact work, Ralph Howerby, and allowing me to go to Antarctica, and a whole long list of research students, Alma College, and I want to thank you for paying attention. And I do have some Antarctica souvenirs if you want to come look, including no Antarctica meteorites, but I do have some real live rocks from Antarctica. If they weren't meteorites, we were allowed to take them home. So I do have some rocks that came from Antarctica. we got mail in the field. And I always tell people it was a U.S. station, so unfortunately it had to get shot. That was my original penguin. I had purchased one to take with me, and after I got back, I had a student give me another penguin, so that's my current penguin collection. And then when I brought all the kind of useful things you take when you go camping, I did bring one really useful item that I never used the entire time I was there because it never got dark. So, questions?
I was just wondering, you're talking about, or you talked about having damage in the thin sections when you cut them. Have you ever considered imaging the fragments of your sample whole in an SE? Like taking fragments of
No, I actually haven't ever thought of doing that. That's not going to get me in the interior to see the porosity is the problem.
Is there any, can you measure the external porosity in there?
What I'm looking for is the internal stuff. So
it's
that's not going to be useful to look at. There's other reasons to look at the exterior, but it's not going to tell me anything about porosity. So,
even if you were to slice through?
If you slice it through, but then you've got that slice damage you potentially are causing that everybody thinks is a big concern, but I think is less of a concern than they think. I mean, these are geologists who look at thin sections all the time. I don't know why they don't know. They recognize the damage. Why can't I recognize the damage? Yes.
The FTIR spectrum that you showed, I may have missed this. Which rock was that of?
That was of a piece of ordinary chondrite that we had put in an oven at 150 degrees for 3 months.
Wow.
So,
Okay.
So with that, and that was like within about a millimeter of the surface. So we had penetrated at least with a millimeter to hydrating it. There didn't appear to be much further in.
Okay, and you were just looking at it from the hydration?
We were just looking for the hydration peak initially. We just wanted to see if it was going to work.
Okay.
And once we realize it works, then I'm going to do some more sophisticated analysis. But if it's not working, there's no point in doing anything else because it's just NWA 869 and everyone knows what that looks like. So I'm interested in seeing the changes in the mineralogy.
Well, from someone who does a lot of FTR, there's a lot of stuff in there like organic molecules.
Oh yeah, I know.
Yeah, that's pretty cool to find those inside the meteorite.
Yeah. Oh yeah, meteorites are famous for their amino acids they find in meteorites.
Yeah, no, absolutely. Yeah. There's a study that we're thinking of doing involving that. So that's cool.
Yeah. And some of that might be contamination from the FTI because it's a shared FTIR. We're a liberal arts institution, so my colleague brings his students down from the organic synthesis lab, and they run things on the same stick. So I have to deal with that kind of problem.
Okay, thank you.
So, yes.
This is totally not my field, so this is a very naive question.
Those are the best kind.
Normally one likes to compare experiment with theory, and for example, your carbonaceous chondrites and the porosity of them. I mean, are there theoretical models that you can compare with what you have experimentally?
People have just started doing these physical measurements on these meteorites. So when you go try to find literature values for this stuff, it's just not there. In one sense, I wasn't surprised with what I was seeing in imagery because the carbonaceous chondrites, they think, experienced aqueous alteration very early in their history out in the asteroid belt, and so that's why they're full of all these water-weathered materials. And so I wasn't surprised to see what I saw. So it was sort of surprising to get high porosities based on what I was looking at. So it's just a question of where the porosity is. And no, there are no theoretical models because nobody's ever looked at the meteorites from this way. They've always done, chemical, geological characterization of the minerals, chemical analysis of what are the different chemicals of both the minerals and of the whole rocks, but have never looked at the materials as a whole, as a material. And so we're starting to do more of that and starting to create models for why we're seeing these differences. You do have, meteorites like Tagish Lake, which you can see is very highly porous. It just looks that way, but these are just whole rocks. There are some that are fairly fragile, so what's holding them together isn't very, very intense. I remember finding a CB3 in Antarctica, and we were being really careful because you barely breathed on it, it started falling apart. We just don't have the theoretical modeling for the physical properties because nobody's really looked at it a whole lot. It's until recently, last 10 years maybe. Yes?
That's the tail off in the size frequency distribution. Is that the resolution of the imagery, or is that your
Yeah, when we get down to the very small sizes, yes, she can get to 1 pixel size in our, in our 4,000 dpi scanner that we've got. So yes, we're looking at the end of the resolution range. So we don't know how much further down it goes. We get a huge amount of the very fine, sandy stuff in the stuff she weighs. Yes.
I have a question about the porosity graph you produced. You have on one axis like the porosity that you figured out using your computer programming.
The imaging, yeah.
So is that like a 2-dimensional porosity that
Yes.
you compare areas?
Yes. Yes.
Now the other technique, does it compare like a volume porosity?
It's looking at a volume porosity, yes.
So do you apply like a 2/3 correction power or something factor?
Not typically.
Because when you I mean, if you're comparing areal porosity, then it's r squared
Right.
for a sphere, right?
Right.
But for volumes, it would be r cubed, would it not? So you would actually just take one porosity and put it to the power of 3 halves.
We haven't done anything like that. I'll see if that.
Because it looks like a lot of your points are a bit higher on
Yeah.
your aerial ones, so I think if you were to do that, it might actually
Improve the data?
Yeah.
Okay, I'll try
might
that.
make a difference.
Yeah, most things metrologists, there is a correction factor you can apply from 2D to 3D because doing this, just doing grain
Yeah.
size analysis.
Right.
It's the same idea,
Yeah,
but there is a correction
I would
factor.
imagine it's between like 1 and 3 halves of the
Yeah.
power.
You have to make it, you're talking about spheres, of course, you have to make assumptions about what shape you're talking about. Usually we're thinking about lath-like things. So here you'd have to make some sort of assumption about what the porosity is.
right,
So you'd have to say, okay, well, I'm going to assume spheres because it's a bunch of
right.
pores in there. Or if it's cracks, that's different.
That's different, and that's mostly what we've got is cracks.
Yeah, exactly. So, but yes, you're right.
That's the problem with all of us doing it as chemists and physicists. None of us are geologists. Yes.
I have a question about your dent measurement. Now, I don't quite see what the big deal is. When I was an undergrad at Laurentian University, I was associated with a dark matter search called Picasso. And we had these bubble detectors. And it was a tiny microscale bubble of droplet of freon in a gel matrix, and this would burst when the dark matter hit it. So we had to, what we did is we thin sectioned our detectors after we pulled them out of the mine,
Right.
and when you image them, they're gray on gray. So you had undergraduates tracing, and there were thousands of microscope, and I don't see why that brute force approach wouldn't.
That's the way we're doing it.
Okay.
It's of the methods we've done, it's the best method.
Yeah.
And we're just trying to figure out if there's a better method.
In the 4 years that I was at Laurentian, everyone spent all of their spare time trying to come up with a way around this.
And didn't find anything.
We couldn't find anything.
Yeah.
But
Yeah.
so if you do come up with something,
let you know.
yeah, I have some friends back there
They're
who'd be
still doing
very
that.
happy.
Yes. Yes.
We're probably hitting time here. I'd just like to, for our thanks to Melissa. I understand that there's another event coming up just now, right at 1:30.